All right, got situated. All righty, so what we're going to talk about in this section is the notion of a function. In fact, the whole chapter is devoted to this notion. So it's actually central to the study of calculus, and so we spend a lot of time on just talking about this idea of a function and its properties in chapter 3. All right, so the notion of a function is basically a way of relating one set of objects to another, right? And so our definition, we give some examples here, but our definition of a function from a set A into a set B is it's some sort of rule that takes every element in A to exactly one element in B, right? And if we denote the element in A that we're talking about by X, then f of X, f parentheses X, is how we denote the value to which it's mapped in B. The subtlety here is that every element in A is mapped to only one element in B. So you can't send somebody in A to more than one place. That's the restriction on a function. Anything else you can think of is fair game, but you can only send every element in your one set to exactly one element in another. So we can actually define functions in different ways. You could have a table of values or a graph or some sort of formula, or you might just have words that describe kind of what you want to define as a function. So let's look at some examples of this. So this function takes every day of the week and it associates with that the number of hours, let's say, that you worked on that day, right? So notice that 7 days in the week are over here. That's set A, let's say, the set of inputs. And we're assigning to every day a unique output that gives you the number of hours that you worked, right? And so this would define a function, right? Plain and simple. Now, had I assigned to Wednesday 6.5 and 4.5, let's say, suppose I had two numbers in this column, then that would not be a function, right? You can only send everybody here to exactly one point over here. All right, so let's look at this one, right? So example 2, you typically don't rely on functions being defined verbally, right? In fact, the minute they're defined verbally like this one, the attempt is to then make it into some sort of formula so you could use it, right? Otherwise, it seems rather kind of useless in some sense. So for this guy here, when we say for every integer, square it and then add 5, what that tells you to do is let's let X be an integer. I'm not going to write it down because I don't have the pen here, but take X to be an integer. The number that we're going to associate with that, the output, is going to be X squared, so we're going to square it, and then plus 5, right, because we're adding 5. So X squared plus 5 would be the formula for the function that would take every integer to that image. Okay. All right, so go ahead and try this. These, you want to try to associate a verbal defined function with an explicit formula. And here, what's going to play the critical role is the order in which these operations are taking place. So order of operations actually from the old chapter 1 or 0, depending on what class you're in, are critical here. So try that, and then we'll talk about those once you've tried them. All right, so for example, here, if you were to look at this one, so for all real numbers X, multiply by 3, so you first multiply by 3, so you get a 3x, then you square that result, you'd have 3x quantity squared. That's h of x, right? If you said it was j of x, remember you have to square the entire 3 of x, and so you need parentheses around that. Let's see. Yeah, so compare that to the third one here. Give me an x, compute the square, and then multiply by 3. So that means you have x squared and then times 3. That would be j of x. You see the difference between the first and the third one. It's the order in which you're doing the operations. For this one, if you subtract the and then square the result, well, here you're taking 3 from x. That's x minus 3 and squaring it. So you get that for part 2. Whereas again, if you reverse the order, if you square the x and then subtract the 3, then we're getting this result here. Okay, so just pay attention to the order in which things are being done so that when you're translating from words to symbols, you do so correctly. All right, so here, a lot of times, especially depending on what field you're in, be it biology, chemistry, economics, finance, any of those guys, you're gonna be deluged with graphs, right? And sometimes, most of the times they'll be functions, sometimes they won't, but most of the time they'll be functions, and you want to interpret the information correctly, right? And so what we're given here is time, where the value of t corresponds to the month of the year. So 0 is January, 1 is February, 2 is March, so on and so forth, up until 12, which would be December. And the y-axis is the number of bear sightings, apparently in some sort of remote part of the United States, let's say. All right, and so what this graph tells you is just how many sightings per month on average there are. All right, so what we're going to focus mostly on in this chapter is functions that are described by a formula, right? And so, for instance, when we have a function in this expressed in this way, so you have an output we call y, and f of x is an expression. It's an algebraic expression like any of these right here. It could be anything that you studied in chapter 1 or 0, depending on what class. Rational expression, polynomials, radicals, who knows what. Any expression involving x, all right? And what we call f of x is the functional value at x. Okay? So suppose I gave you this function here, f of x equals x squared minus 3x plus 1. And I wanted to know what number that rule maps the x equal 2 to, right? So a 2 is my input, and I want to know what value does it map to. Like back here, remember with the table, right? If I wanted the image, f of Tuesday, right, I would say f of Tuesday is 8. That's the output that Tuesday is linked to. Same way here, oops, I just now have a number in and a number coming out instead of a qualitative sort of function. So to find f of 2, all I have to do is plug a 2 in for x everywhere I see that in the formula. So for instance, f of 2 here is 2 squared minus 3 times 2 plus 1. The minute you compute that, now you use your order of operations to simplify. Okay. Same way if we put minus 4 in for x, everywhere I see an x in this formula, I put a negative 4. Just be careful there with negatives because you want to make sure that you perform the operation on the entire input. So I need to put parentheses around that negative 4 to make sure that I square the minus 4. And then same way here, if you don't put parentheses around that, it's almost like you're subtracting 4 from minus 3 instead of multiplying them. So be careful and diligent with parentheses. But aside from that, it's pretty much that simple to compute a functional value at a x value. All right. So here, let's look at a slightly more, it's not harder. It's just that people get confused by it. Let's put it that way. So let's look at this example. You have another quadratic function. And suppose we know how to compute f of negative 1. No worries with that. But f of a plus 1, right? So you want to think of that. You know, say, well, what are you talking about? I thought you only put numbers in. Well, remember, algebraic expressions represent numbers the minute you assign a value to that variable. And so this is perfectly valid. I can put that in and compute its functional value to get an expression that involves a, right? There's nothing wrong with that. But people often confuse how to do that. And so what I want you to think of until you're used to dealing with these sort of functions is rewrite the function with, instead of an x, I'm going to replace the x by a box everywhere I have it. So I have a box for the input here, and I'm going to replace the x's here by boxes. Now, to compute f of something, all that means is whatever the something you want to plug in here, be it negative 1, 5, or a plus 1 in this case, whatever's in that box, you replace each of these boxes by the exact same thing, right? And notice that's what we did up here with f of negative 1. We put a negative 1 in for x here and for x there, which is exactly the location of these boxes. So if I want f of a plus 1, there's no difference in the approach. You plug in a plus 1 in each of those boxes, okay? And then on the right side, once you have this, that is an algebraic expression that you can simplify using the rules of algebra, right? We know how to square a binomial. We know how to distribute a number through a trinomial and a binomial, so on and so forth, right? So the newest part that causes heartburn is right here, right? Whatever's in the box clunks into the box over here. Don't be doing any sort of crazy things with this f, right? You're not multiplying these. This is an input, right? So you cannot distribute the f. Don't say this is f of a plus f of 1. You cannot do any of that. This is simply a whole thing that cannot be chopped into pieces by doing anything with this function. All right. Now to see the simplification, once we have here, all I did was I FOILed this part out, right? And then I distribute the -3 and the 2 and then added like terms, right? But this here, like I say, is the part that causes the most grief. All right, so go ahead and look at these few functions and try to compute these functional values just at numbers, just to see what you get. And then, so pause the video, do that, and check yourself here momentarily. All right, so f of 0.5, I'm going to put a 0.5 in for x, 1 over 0.5. Well, remember 0.5 is a half. 1 divided by a half is 2, right? That's how I'm getting that. For this guy, g of -6, well, g of x equals 5 is a constant function. What that means is that no matter what x value you give me here, be it -6, 0, 10 million, the output's always 5. Right, and so, you know, you look at this and you say, well, where do you put the x? I mean, there is no place on the right side to put it. But that simply means the output is 5, right? The value of x doesn't change the output. And so you just get 5 in this case. For this guy here, h of 0, plug a 0 in for x. That's what I do here. Simplify to get -3. And then finally, j of -2, I'm plugging a -2 in for x. Do not forget to square the -2, right? If I square -2, this becomes 1 over +4. 1/4 is 0.25, so in the end you get 1.75. All right, so in terms of notation errors, I already talked about one of these above. You cannot distribute the application of a function across a sum. So for instance, when what I was talking about the f of a plus 1 business, you cannot say it's f of a plus f of 1. Just don't even do that. This is not multiplication. This is f of some object, right? So you can't do that. Don't treat it like a variable. Same way here. Basically, this is the same idea. You cannot distribute f through a quotient or a product, right? So it's just a single object. And likewise, if I'm dividing two functional values, you can't just cancel the f's, right? Again, these are not being multiplied like they were when we talked about rational expressions. These are functional values. They're outputs that are associated with these inputs A and B. And so you can't just cancel them. Okay? On your own here, I don't have extra examples. I provided them in the example. But you want to actually create your own examples just to cement these ideas in, that these quantities just don't hold. All right, let's try. Oh, okay, so let's look at example 5. So I can show, eventually we will actually graph this sort of thing, but you can prove that this is a function. If you give me a single x, there's a single output, right? So that can be done, don't worry about that. But if I wanted to compute some functional values, we know we're kind of pros at this now. We can plug in 1 for x, we can plug in 2 for x. But what if I told you to plug in -1 for x? Right? If I try plugging in -1, I get -1 here, which is fine, but then I have 2 over 0. Right? And we know what we can't do is divide by 0. And so apparently -1, if you plug it in, you get some undefined expression. What that tells you is there's no output for -1, right? And that's going to happen, right? So not every time will a function be defined for every real number. And so what we want to do is gather together all of the real values that for which the function does have a sensible output. And that set is called the domain. All right, so what I want to do is, given various expressions for f of x, I want to first determine what the natural domain is, the biggest subset of the real numbers for which there are sensible outputs, just so that I don't have to worry about can I compute this or not, or I already have in front of me which values I can actually compute the functional value of. All right. And then for all those, if I gather together all of the outputs in a set, we call that the range. All right, so let's look at example 6, right? The only number that causes grief on the right side is the one that makes the bottom 0. And so -1 does not belong to the domain, but every other number you give me provides a sensible expression, right? And so the domain here, the natural domain, is every real number except for -1. And so if you think about what that looks like on a number line, you have a full number line, and then you'd have at -1, you'd have a open hole, right? And so if you want to write this using interval notation, start at -1 and go to the left, that gives you this guy. Start at -1 and go to the right, that gives you that guy, and then union them together, right? That set is the domain. All right, so next for another function, what if I consider square roots, right? Now, when we talked about radicals before, we noticed that if you happen to have a negative radicand and you're taking a square root or a fourth root or any even index root, you're going to get an I. And what we're not going to allow to have happen now is there to be an output that involves I, right? We want to look at real valued functions, which means they take real numbers to real numbers, right? Because we want to be able to graph them. And when there are i's involved, the graph just doesn't behave the same way, right? And so we're not going to allow imaginary outputs. That said, the only way you're going to get an imaginary output for a square root is if you take the square root of a negative number, right? So to avoid that, I'm going to insist on the radicand, 3x plus 2, being non-negative. It could be 0, right? If it's 0, the square root of 0 is itself 0, right? So that's perfectly well acceptable. And it could be positive, right? So I had to solve this linear inequality, just subtract the 2 and divide by 3, to get what x values I could plug in here to ensure that I get a sensible real output, right? So in this case, everything to the right of and including -2/3 is in the domain. And so I have this right ray that's closed on the left side as the domain. All right, let's go ahead and try these, right? So 3 functions, you have rational expressions and radicals all tossed in. See what you get, right? So pause the video, try to do these and see what all you get, and we'll talk about them when you come back to the video. All right, so let's look at the first one. It's purely rational expression, polynomial over polynomial. And so the only time rational expressions are not defined is when the bottom is 0. The bottom's already factored. And so we know that a product of real numbers is 0 only if one of those numbers happens to be 0, right? So x could be 0, x plus 5 could be 0, or x squared plus 1 could be 0, right? And if any of those is 0, then we're dividing by 0. That's no good. All right, so, well, if x is 0, then we have to throw 0 out. The number that makes x plus 5 0 is -5. So we'll need to throw that out from the domain. And here, x squared plus 1 is always it's always positive. In fact, it's always bigger than or equal to 1, no matter what real number x you put in there. And so it's never 0, right? That's not going to give you any point to remove from the domain. And so the only values we're throwing out are 0 and -5. And so the intervals that I get, if you think of a number line, you'd have a number line with 2 holes, one at -5, one at 0. And so the intervals in between are all part of the domain. All right. For the second one, this is basically just like example 7 that we talked about, right? It's a square root. So in order for this to produce a real number, the inside has to be bigger than or equal to 0. If you solve that for x, add 7, divide by 4, you get this right-hand ray. Right? Keep in mind, had this been a cube root, you can take the cube root of negative numbers, right? Because if you cube a negative number, you get a negative number back. So just be careful. Cube roots, the domain here would be all real numbers, right? If I had the fourth root, same story. The inside has to be non-negative. So it's just a distinction between even and odd index radicals here. And j of x is very similar to h, but now I'm dividing by this radical instead of just having it in a numerator. So we have an additional restriction, namely that the radical itself cannot be 0, right? Not only does the radicand have to be non-negative, I cannot put the x value in there that makes it 0 because the square root of 0 is 0, and I can't divide by 0, right? So here, the only extra restriction over part 2 is I have to now throw out 7/4, and so now I get this open right-hand ray. All right, so let's take a look at this. Now, what if we start throwing them together? Right, you can form functions by plugging anything in for these algebraic expressions. So what if I have both of these radicals and parts in the bottom? Right? Well, you handle one restriction at a time. There's no difference in the approach. You just have to get more restrictions is all. No big deal. So look at the bottom. The bottom cannot be 0. And so I have to throw out both 0 and -5, just like I did here. Furthermore, in order to produce a real number, I need the radicand here to be non-negative. So I need 1 minus x to be non-negative. Right? So I need this condition too. But if I solve that for x, add the x to both sides, you'd get 1 bigger than or equal to x. But remember, you read inequalities from the variable. And so 1 bigger than or equal to x corresponds to x less than or equal to 1. Okay, so if you were to graph all of this on a single number line like I did here, you would start at 1 and shade to the left. That would be a left ray that corresponds to this piece. But then you also put open holes at 0 and at -5 like I did, right? Because I can't allow those values in, I'd be dividing by 0. And so in interval notation then, I have this guy here, which is this piece. I have the piece between -5 and 0. That's this open interval. And then I have the half open interval from 0 to 1. And I'm simply unioning those together. All right. Your turn here, same idea. Let me just talk you through briefly and I'll let you check it on your own later. You can't have, the bottom can't be 0, right? So I have to throw out x equals 2 and whatever makes that guy equal to 0. And don't forget, you have to, since this is a even root, you need the inside to be non-negative, but it can't be 0, right? So you're going to solve the inequality 2x plus 1, oops, strictly positive, right? And so we know that x has to be bigger than -1/2 and x cannot be 2, right? So you have those two conditions that have to hold. Notice I didn't do anything with the x plus 1, right? That's in the numerator of the fraction. It doesn't itself have a square root around it. So there's no value of x that makes the numerator undefined, right? You can have a 0 up there. 0 over a number that's not 0 is equal to 0, right? So in other words, 0 over 5 is equal to 0. That's defined. And there's no reason it can't be negative because I'm not taking the root of that. And so I only have the two restrictions, x not 2 and x bigger than -1/2. You always want to try to draw those on a number line. And so you have the open interval from -1/2 to 2, and then from 2 to infinity unioned up. All right. And then example 9, I'll let you read on your own. It's just a matter of computing with functions and interpreting in context. So it's kind of getting you geared up for what you consider to be word problems, but now using functions to model them. All right, so I'll let you read that one on your own. And then your turn 6, let's actually talk about your turn 6. All right, so the cost C of x of manufacturing X hard drive is defined to be that guy, 55 plus 10x, and it's assumed that the units are in dollars. All right. We know how to compute C of 4. you simply plug in 4 for x, right? So that's what I do here. And now, well, what does that number tell you? I mean, it's a number, 95. So what? Well, remember what C of x represents. It's the cost of manufacturing X hard drives. And so here, since X is 4, this $95 is the cost of manufacturing 4 hard drives. Okay, that's the interpretation of that function. All right, units are very important, right? So that's true no matter what field you're in. We don't want to do this in a vacuum, although sometimes just with computations, like in algebra, just to get you used to the rules, we'll have the, we'll just have you do this stuff outside the context of a real world problem, just to get you adept at working with these expressions. But the minute you're in a real world problem, you have to account for units. It'll help you interpret what the meaning is. All right, and so part 2 here, what is meant in this context by a solution of this equation? Well, remember, C of x represents the cost of manufacturing X hard drives. If that cost is equal to $455, what a solution would be is the number of hard drives X that you could manufacture, so the cost would be $455. Okay. Think about that. All right, so once you're done with the video and you feel good, go ahead and try the problems. Again, remember these are in the PDF of Chapter 3, Section 1, if you're in pre-calc, other section, or if you're in 115 or 113, if you're in pre-calc, it's in Chapter 1. So go ahead, try these problems and let me know if you have any issues. All right, take it easy, bye.